Hello and welcome to College Algebra Coronavirus Edition. Woo! Or should I call it Quarantine Edition? Ooh, that's better. I like that. College Algebra Quarantine. Something alliterative. Anyways, since we are not finished with the year, we're a college level class. We got to keep going, which means we're going to be looking at the next chapter. We finished off before we left, going through chapter 4 or chapter 3. We had finished off with talking about inequalities and talking about transformation functions. This chapter, we're going to be looking at linear functions. If you're looking at your textbook, this is on page 280. If you're looking at your PDF, it's on page 298, which you can see on my screen. I'm going to be going through some terminology, working through some examples, and at the end, I will post the homework assignment, which will be due at the end of the day on Saturday, as will all future homework assignments while this quarantine is in effect. I hope this thing finds you well. I hope you're staying safe and that you make sure you dedicate some time to keep up on your math. This is a college level class. I know you guys have other things on your mind, but this is happening. So let's go ahead and get started. Chapter 4 is a relatively short chapter. It's only got 3 sections in it, and they all deal with linear functions. This first section is the big one, and you can see in here how it's got a grand total of 7 talking points we're going to go through. Representing a linear function, determining whether a linear function is increasing or decreasing, interpreting slope as a rate of change, writing and interpreting an equation for a linear function, graphing linear equations, my favorite, determining whether lines are parallel or perpendicular, and writing the equation of a line parallel or perpendicular to a given line. We're going to go through each one of these today in the time we have, and by the time we're finished, we'll have an example of each one and discussions on how to do each one in turn. So let's start with the basics. 1. Anytime we want to start off, we want to make sure to have some clear definitions of what we're talking about. So let's define this phrase, linear equation. So a linear equation is simply an equation that has a constant rate of change. All equations change over time. If you look at a picture or a graph of any kind, you can see that all equations change. As we move from left to right, change occurs. Otherwise, it wouldn't be a function, it'd be a dot or a piece of a line. And so when we talk about a linear equation is simply one very specific example of these, a subgroup, if you will. And this subgroup is one where the change is constant. Over time, the same amount changes as we move left to right. In other words, if we pick any interval, say from here to here, and calculate, well, how far did we travel versus how much did we go up and down, that amount is going to be a constant. It's not changing. No matter where we pick, if we pick a different interval, it's going to have the same constant amount changed. Now, when we talk about linear functions, it's important to note that you can talk about them in a couple different ways. Let's start with the beginning. 1. In words. I think this is the least useful in terms of the high school level, but the farther you want to go in math, the more important it is to understand the word version of every problem. And so let's read through this. The train's distance from the station, and I'm right here in the text, at the bottom of page 280, is a function of time during which the train moves at a constant speed, plus its original distance from the station when it began moving at a constant speed. You can always tell a linear equation if it mentions constant with respect to the change. So the change in this case is speed, and it says the speed is constant. That tells you it's going to be a linear equation. What's happening is, when we talk about a linear equation, looking at a constant, it's called rate of change. And for the rest of today, I'm going to use an abbreviation, R of C. Rate of change, or if you prefer, a different term we've talked about before, slope. We talk about linear equations, we talk about a constant rate of change, meaning how much it is changing over time is the same amount, no matter where you look. We can look as far to the left as we want, as far to the right as we want. It does not matter where we look. How much it is changing is constant. So this is a linear equation. In terms of words, the common words we use when we talk about a linear equation are constant, unchanging. Any of these can be good options when it comes to talking about a function that is linear. Various examples of this can be seen in the text, but now I want to look at the more common one for us, which is going to be in linear notation. There are a couple ways to write linear functions. The common way we see in algebra is in what I like to call the standard linear form, y equals mx plus b. This is a great equation. It's very common to see in Algebra 1 classroom. Since we've already discussed it, though, I want to make a modification to the more common one used in upper level mathematics, the function notation. Remember, a linear equation is a function, so we use this modified version. F of x is equal to mx plus b. This version, you notice, is exactly the same with one change. Instead of having y as a new variable, we represent y as a function specifically of the old variable x. And so when we look at this function, you can see that it labels the rate of change as m, the variable in question is our x variable, b indicates what we're going to call the intercept, and then it all represents this functional notation. And so the function is changing with respect to x by a constant amount starting at a location b. So this is our functional notation. You may be used to this old one, but we are going to start using this new one much more heavily. That does not mean the old one is going to disappear. It means more often than not, this bottom one will be how we write it. I want to point out in our book on a very important detail here, one of the first clear examples of this functional notation of a linear function. It uses this notation, d of t is equal to 83t plus 250. Now, in this case, we know this is a function with respect to t. So this tells me that t is the variable, and d is what's being changed. This is the output, or what we call the dependent variable. T, in this case, is what's being changed, what's being plugged into. We have here the 83, that's going to be our m. The 250, that's going to be our b. And the t is what's changing over time. This is the exact same function notation, but instead of using x as our variable, we're using t. And for this example, it makes much more sense to use t, and that is because of the example it talks about. We're using something with respect to time. With time, we want to make sure to keep track of time in the equation, so we use t for time. If we use x for time, that can get confusing later on, because if we have another variable for tracking xylophones or something, we don't want to confuse the xylophone variable with the time variable. So we use t instead of x whenever it's necessary. You could always rewrite this into function notation that has x in it, but it is far more common in mathematics to fit the variable to the situation, not the other way around. The last one I want to showcase is this table form. Now, this table form is unique because we don't commonly see this in a lot of lower level mathematics. So let's take a look at this table. In this table, you'll notice a few details to point out. One, we have the t and the dt as rows going left and right. The t is increasing by 1 every single time. So notice how much we are changing is constant. Notice that the bottom number is also changing by a constant amount, when the top number is changing only by 1 each time. Each time we're adding 1, each time we're adding 1, each time we're adding 1. The bottom number each time we're adding 83. This tells us it is a constant function, because we have the same amount changed on both the independent and the dependent. Notice they are different amounts between each other. Ones are 1s and the others are 83s. But each time it's constant. 1, 1, 1, 83, 83, 83, constant, unchanging. This means we are dealing with a linear function. Okay, lastly, everybody's favorite part of mathematics is graphing. I know it is for myself anyways. And if you feel differently, get over it. Okay, with a graph. Anytime we talk about a graph, it's important to note what the graph of a linear function always looks like. The graph of any linear function will always look like a constant, meaning as the x variable changes, it forms a line. That is why it is called a linear function. The word linear in Old Greek means line. And so this is an example of the line f of x equals x, meaning as x changes, the f of x values change by the exact same amount. Here's my x-axis, and here's my f of x axis. So this is a linear function. It's a linear function because, well, it's a line. Now, when it comes to linear functions, you can always spot them by looking at individual points and comparing them and saying, is this a line or isn't it a line? It needs to have constant change, which again means that if I pick any locations and say, okay, how much is the x value changing? How much is the y value changing? We can compare those two and see if it is a linear function. And that same process works anywhere on this graph. If I pick this first grouping, I'm going to get an answer for how much it is changing. If I pick a different grouping, like say this grouping, that same amount is going to be found when I compare these two groups, just with different x's and y's. The x's and y's will change, but overall what won't change is how much they have changed. It is going to be constant. The amount we have adjusted over time is the same, which makes this a linear function because it is constant. Okay, so far we've discussed big details. 1, the definition of a linear function is a function that has a constant rate of change, meaning that anytime we look at it, it is one that is a linear function in terms of a line. It usually has two different forms, either the standard notation using y's and x's, or the functional notation using f of x and then your function itself. This can be written with any variable and with any functional note. So in this case, we have a dt example. It can also be found using a table or with a graph. So these are the big first steps to going forward. So make sure you have a solid grasp of these couple of concepts before moving on. Again, definition of a linear function, the two types of functional notations, what those functions look like, how that can appear in a table. Okay, next piece. Anytime you talk about a line, the next piece of algebra comes up. Beautiful line, thank you. All right, rate of change. As I prefer to abbreviate it, RFC. Or if you're really fancy, slope. Now, the rate of change is an indication of how this function is adjusting over time. The rate of change is a number value. This number value helps to indicate how the function is acting. In other words, what we call behavior. Is the function going up over time? Is the function going down over time? Is it doing nothing, having no change, or is it doing something else? These 4 different basic concepts are the 4 different categories we can talk about. A function can be increasing, meaning that over time, and when we talk about over time, we mean from left to right. So as we talk about the rate of change, we are always assuming we are working from the left going to the right. Where left? Any point we pick can be the left point. And then as we move to the right, what is happening? Is it going up over time? Is it increasing? Is it going down over time? Or is it decreasing? Is it making no changes? Meaning it is not going up and it is not going down. In other words, is it constant? Or is it something we refer to as undefined? Meaning it is not changing over time. Meaning instead of moving left to right, it is moving straight up and down. So each of these indicates the rate of change. And again, these all assume we are working from the guise of left to right. If we pick any points, we can say from left to right, how is it changing? Going back to this picture. We would claim this line here in red is an increasing function. Because if I pick any point on this line, let's go with this point, and I move to the right, it's going up. So it is increasing. Again, I can do this anywhere on this graph. I pick this point, as I move to the right, it is still going up. So that makes it still increasing. And again, this is a property of linear functions, is that it's always changing by the same amount. So if it's increasing down here, it's increasing up here as well. Compare this instead to a slightly different version. Let's go with one over here. Make a new function. Okay, this function we would say is decreasing, because if I pick any point on this graph and move from left to the right, how is it changing? Well, it is going down. As I pick any singular point and I move to the right, What happens to the function? It goes down. We would call this function decreasing. It is always important to note the two major differences between any set of functions. This function is a visual representation of an increasing function. The other function is a visual representation of a decreasing function. They are both lines. They're both linear functions. They both have a constant rate of change. But the question is, are they increasing or decreasing? How are they changing over time? In terms of realistic examples, increasing, decreasing, constant, and undefined are very basic concepts. They need to be understood, but they are also predictive. If I tell you a function is increasing and then give you a dot right there and say it's increasing, well, that means that I know to the right of this dot, it's got to be going up. How much? Well, that could be determined from a formula. How fast? Again, it's a formula. But I at least know how it is changing at that most basic level. It is going up. Maybe it's going up slowly, or it just goes up just a little tiny bit. Or maybe it's going up very quickly. But in each of these examples, all three of these are considered to be increasing. Because as we move from left to right, they are going up. Okay, rate of change. We've already discussed once the definition of rate of change. It's a number value. It's how the function is behaving. And it's closely aligned with this concept of something called slope. So let's review slope. In mathematics, we refer to slope in a couple of basic ways. And I go a little out of order of the book, so I want to make sure to showcase both parts, and I will come back to this piece in a second. But let's talk about slope. In our formula, over here, slope is considered to be m. It is the rate of change. So in my formula here, I want to make sure to recognize the slope as the rate of change, and it's represented by m. There are a few different ways to write slope in mathematics, and each of these ways is dictated down here in our definition in the book on page 283. We have rise over run. We have delta y over delta x. And the far more standard y2 minus y1 over x2 minus x1. All three of these are the same thing, and probably one of the most important pieces from this homework assignment. You need to know slope. You need to be best friends. If you have other best friends, tell them to take a hike for a couple days. And it's nice outside. Please do so. This is the slope. We need to understand slope at a fundamental level, and each of these has to do with different things. I like to think of this first one as being really helpful when I'm looking at a graph or a picture. Because rise, I can see, it's visual. Run, I can see, it's visual. So this, to me, tells me when I'm looking at a picture, I want to look at rise over run. The delta y over delta x is the standard definition. And how we get that definition is from what's referred to as the formula definition. The y2 minus y1 over x2 minus x1. I'll make a bigger version of this because this is the most common one we will use right here. y2 minus y1 over x2 minus x1. Again, this is slope. One of the most important equations from this chapter and from this section in particular. Now, how do all two of these link back together? Well, it's very simple. If m is bigger than 0, this means that in my picture, we're going to be increasing. If I have an m that is, for example, 2, so y equals 2x minus 3, the m in this case is bigger than 1, which means that for this function, my rate of change means that I am increasing. I know now, in my head, a rough idea of what this picture looks like. Over time, it is going up as we move from left to right. Again, left to right being key. This is an increasing function. If instead the m is less than 0, in other words, if the n is negative, we would call this function decreasing. A decreasing function might look like this. Y equals negative 3x plus 4. In this case, the negative 3 is our m value from our old formula. And that negative 3 tells me that this function has a rate of change, which means it is decreasing. because that m is less than 0, it is decreasing. And the bigger or farther away this number is from 0, the more it is increasing or decreasing. If I have a 20 here instead of a 2, that means that over time it is going up much faster compared to just a 2, or a 1, or even a smaller number like a fraction. This -3 tells me that it is going 3 times as much down as it normally is. So we can use this information to get a rough idea of what this picture would look like, even without having the picture in front of us. This is the advantage of knowing and understanding rate of change, is I can get an idea of what this picture looks like without needing to get the picture, which is big. Because if you don't like graphing, you want to do whatever it takes to get rid of the graph. This is how. So, the last one we need to talk about, what if m is 0? Well, if m is 0, we call that constant. And if m is 0, it's weird. It makes the function look a little different. Y equals 0x minus 6. It turns out that function will never be written that way, because 0 times x simplifies. So usually you'll see it written as y equals -6. Because there is no m, we assume the m is 0, meaning this has a rate of change that is constant. You will never see it written in this form, because we simplify things in mathematics. 0 times x, the x goes away. So you will only ever see it written in this form. You have to recognize that y equals -6 means you're dealing with a constant, meaning that over time, it is not changing. Always refer to these images in your brain whenever you look at a function and ask yourself increasing, decreasing, constant, or undefined. This tells me that this function will look like this, just somewhere in the graph. The final one is an undefined function, and in this case, the undefined function, it's best to consider it when looking at an example. X equals 4. X equals 4 is an example of an undefined function. In this case, the 0 in question comes from 0y. If we were to take this equation and rewrite it to solve for x, we would end up here. Notice that the y has disappeared. Notice that these two, constant and undefined, appear to be opposites. The constant function has managed to get rid of the x values, whereas the undefined function has managed to get rid of the y values. This is because how each one acts. With a function like this, it is considered to be undefined, because the y is not defined. And remember, the y is what determines the rate of change. So, this is an undefined function. All right, there's our 4 big components to talk about of rate of change before we get into the meat of today's material. Increasing, decreasing, constant, and undefined. And we have here examples of each. This represents an increasing function. It is increasing because of the 2. Since the 2 is, in fact, bigger than 0, we would say this is an increasing function. Whereas in this example, we have a -3. Since the -3 is, in fact, less than 0, we would say this is a decreasing function. In this example, we have a slope of 0, which is often dropped because 0 times anything makes it 0, which makes it a constant function. If you see a function that does not have x in it and just has a y by itself, no y squareds, just y by itself, it's constant. If you see an x by itself, no x squareds, it's undefined. Always and forever. So, first big points to make out. Now, when it comes to rate of change, before we can go forward, you should note, anytime we talk about rate of change, we can talk about it from the conceptual in 3 different ways. We can talk about it using the equation, which is the most common. If we look back at this example, we would say this function is increasing. 83 is our slope, our rate of change. 83 is in fact bigger than 0, which makes this increasing. We can also look at that from the table's perspective. But when doing it from the table's perspective, it is best to use this formula. Because with this formula, we can plug in x's and y's, or x's and f of x's, and get a solution. Before I go forward, I want to point out something in the text that I think is really important. This example. Take a look. It's at the very bottom of page 283. It is a variation on the slope formula using function notation. It is the exact same formula. Do not be convinced otherwise. These two are equivalent. Because remember, y is equivalent to f of x. We saw that before, when we looked at function notation before. Y and f of x are essentially the same. So if we look at y2, it's f of x2. The 2 stays constant, the y changes to f of x. Now, both these versions will be key to moving forward. Make sure you know them and know the connection to how we describe them using rate of change. Increasing, decreasing, constant, and undefined. Whew. Okay, so before we go any further, let's do some examples. Fresh piece of paper. Boom. Okay, we're going to do one of each real quick. These are the same examples that are in the text, so you can use the text to follow along. In this case, we're looking at example 3, which can be found at the bottom of page 284. The thing says, if f of x is a linear function and 3, -2, and 8, 1 are points on that line, find the slope. It is a function increasing or decreasing. Now notice that they've dropped the other two terms because it is very uncommon to have a constant or undefined function. They're less likely and less interesting because they're simply not changing in the same way that a function can be increasing or decreasing. We always, as humans, want things to be changing, either going up or going down. When they stay the same, we get bored. Maybe you're finding that at home now. Notice that to do this, they are using the slope formula first. Afterwards, they are analyzing the slope formula to determine if it is in fact increasing or decreasing. Let's do this. So they've given us 2 points, the point 3, -2, and the point 8, 1. We're going to use these 2 points to determine if it has a slope, which it will because it's 2 points, and then we're going to see afterwards, is it increasing or decreasing. Now, to use this form, we're going to use the function notation f of x2 minus f of x1 over x2 minus x1. Remember, this indicates your y value of the second x number divided by the x number's second, and then f of x1 and x1 respectively. So over here, I'm going to use this as my x2, this is my x1. That would make this f of x2 and this f of x1. So let me go ahead and plug them in. I take f of x2, which is 1, minus f of x1. f of x1 is -2. I'll put the negative in parentheses. I don't want to confuse these two negative signs. One is a negative sign from the formula, one is a negative sign from the problem. Now, I do the x values. That is 8 on this one, minus 3 on that one. Note we keep the 8 and the 1 together. Just the 8 goes on bottom, the 1 goes on top. We keep the 3 and the -2 in together. The 3 goes on bottom, -2 on top. Consistency is key. Keep them together. Not on the same line because we do x is on one line and y is on the other. Now we start simplifying. The double negative makes it positive, so we have 1 plus 2. And then 8 minus 3 on bottom. 1 plus 2 is 3. 8 minus 3 is 5, which gives me a fractional answer, which is perfectly acceptable. But I'm also going to write it as a decimal, 0.6. Why would I do that? Because this tells me the slope, which was the first thing the problem asked for. Now we need to answer the second piece. Is this increasing or decreasing? It can't be both. It is not possible to be both going up and going down at the same time unless you're ripping something apart. And in math, we don't do that. That's, biology. So, increasing or decreasing? Well, the question becomes to analyze this number. Is this number bigger than 0 or is it smaller than 0? In other words, is it positive or is it negative? What we can see from here, 0.6 is bigger than 0. That means this function is increasing. If this had been a negative number, like say negative 0.6, we'd call it decreasing. It's an important thing to note down here at the bottom. We chose to put the 1 first and the 8 first. We chose to put the negative 2 second and the 3 second. It does not matter which order you do it in. If we had done negative 2 first and the 8 second, we will end up with the exact same solution because that's how algebra works. Double negative makes it positive, same answer. It does not matter which order you go in, provided you follow the rules. x2 and f of x2 have to go first. F of x1 has to go second. They have to be kept together. If you flip-flop these around, you're going to get the wrong answer. All right. Next. Writing and interpreting a linear function. Anytime you look at a linear function, you can determine a couple of basic factors about it. You can determine the slope. You can determine intercepts. But in order to do so, you have to be able to analyze and interpret. That is a key component of today. You have to be able to look at a picture like the one here and ask yourself, how is it acting? What is it doing? Answer basic questions. Is it increasing? Is it decreasing? How can I find points? Each of these is not always an easy question to answer. So taking the time to do so is very important. So let's take a look at our two components here. First one. You can see in this graph they've detailed out two specific points. And we're on page 285 right now at the bottom of the page. These 2 points are important because they can tell us how to find the slope. Remember, when it comes to a linear function, we have a constant rate of change, meaning the slope never changes. Or, in other words, they chose to use these two. If I chose to use this dot up here and a dot down here somewhere that's also on that line, I'm going to get the same answer. It does not matter which points I choose. There are infinitely many points on this line. You can choose any 2 of them, and this negative 3 over 4 is going to pop out. You need to be comfortable with that knowledge and take that knowledge to get to that next step. So, they used it to find the slope first, which they've done by using that formula. Notice that they used the y version because this function is in terms of x's and y's. And so they plug into the formula and pop out the slope. Yay. And now they use the second piece. Now we haven't talked about this yet, but there are a couple different ways of writing the function that are really common. This first one, y equals mx plus b. This is typically referred to as slope-intercept form. Very common in mathematics. Why? Because y is by itself. We like having one of the variables solved for, and in this case, it's nice having this function written like this. And also because this is the best way to get it in function notation. It's the easiest one to keep in function notation. And so this becomes a very popular form to use. There is a second one. Y minus y1 equals m x minus x1. This is referred to as point slope. While the top one may be popular, this one is more widely used. We like the top one for how nice it is. We like the bottom one for how useful it is. You may love your nice truck or your nice sporty little car, but if you have to get a bunch of people to a place, it's not always the best one to use. Sometimes you need the minivan, and this is the minivan of math equations. It'll get you there. It ain't going to look pretty. You ain't going to like it all the time, but it's the best one for a lot of situations. But being able to use both is really key. Notice that for this function, once they've got that function listed out, they then, using the slope and one of the points, plug into this form. That's key, because they have to make a conscious choice as to which point they want to choose and have a slope to plug into it. Each of these functions requires 2 details. This one requires you have the slope and the y-intercept. You can use it if you have those 2 things, or if you can find them. This one requires you have the slope and exactly 1 point. But again, there are infinitely many points. You just have to choose one of them. Now, I am a huge fan of leaving this function in this form because it's correct. It requires no extra work to get to that solution. However, the reason we take the time to solve the other one is because the other one is equally important. In this case, they've used y minus 4 equals their m, negative 3/4, x minus 4. If you were to solve this equation, you will solve and find a similar equation. And that point was, nope. That would be a 7. This would be a 0. There we go. If we choose to use the first point versus the second point, there is a breaking point where they become exactly the same. If we solve this top one, as you can see on there, we get y equals negative 3/4 x plus 7. You can watch their steps and see how they do it. They distributed, they move the 4 over via addition, and simplified to get that form. If you do the same thing to this bottom equation, you will get the exact same equation. This is the other reason this top form is so well liked. It always gets the same result. These two equations look different. One has double 4s, one has a 7 and a 0. They look different, but they get the same y equals mx plus b form. So again, while this bottom one was very useful because it's very versatile, it can do either one, the other form is the one that's better because it can do both at the same time. This top equation and this bottom equation are the same, despite them looking different when we have it in the other form. If you're like most standard math students, you don't like when things look different. You do not like it when they have different components and different qualities to them. And that's an advantage when it comes to this top equation. It will do both. Okay. Going on. How to write an equation. There's some steps you should follow anytime you need to write an equation. If the instruction ever says write an equation, there are some basic steps you need to do. Step 1. You need information. So you need to know what is given. I need to check and see, am I given 2 points? Maybe if I'm not given 2 points, can I find them in a graph? That's key too. Because if I can't find 2 points, I need to move on to the other option. Do I have 1 point and the slope? Or do I have the intercept and the slope? It has to be one of these three. And even if it doesn't look like it, it is one of these three. Take a look at this picture from example 5 on page 286. We can see that there are a couple points we can use. And in fact, they chose 2 of them, 0, 2, and negative 2, 4, as the 2 they were going to choose. Notice that that was not in the original problem. The original problem is just this, right here. No points listed, no indication of how to do it. You have to take the steps. So they saw, I got a point, and they choose to use this first process. The first process states, if you have 2 points, use those 2 points to find the slope. Once you have the slope, you're going to plug slope and 1 point into point slope form. So, take a look. That's exactly what they do in example 5. They aren't given 2 points, but they can find 2 points. And they did, these 2. They used those 2 points to calculate the slope. It's 3. They then plug 3 and one of those points into this function. And don't forget to simplify. Very important. If you have 1 point and the slope, well, guess what? You're in luck. Skip that first step. Go ahead and plug in to point slope form. Again, if you were already given a point in the slope, don't bother finding the slope again. That's a waste of time. Just plug it in. And of course, simplify. Pay very close attention to your instructions. If you're given the y-intercept in a slope, you can instead plug into slope-intercept. And if you do this correctly, you won't even have to simplify, which is super convenient. Oh, it's so nice. If you like doing less work, oh, do this one. Now, all three of these methods work well. You have to be conscious of the problem and ask, which one's the best? And the example I have above, they don't come out and tell me any points. They don't come out and tell me the slope. They don't come out and tell me the intercept. So I have to make choices. And it decided to do the top one. It found 2 points, which is relatively easy to do when you're given a graph. Use those 2 points to find the slope. Plug that slope into point-slope form, and then simplified. And you can see all those steps listed out right here. If we had been given anything else, we might have chosen a different process. It's just the way it works. So you have to be willing to take a look at a problem and say which is the best. Looking at this one here, it's the exact same figure, but with the 2 points labeled. That makes it much clearer that you should probably use that form. But you have to look at a problem and ask which one's the best one. Now, oftentimes you're given a word problem and you have to infer some information. In this case, look at what this says. Suppose Ben starts a company in which he incurs a fixed cost of $1,250 per month for the overhead, which includes his office rent. Anytime you're looking at most word problems, 90% of what you see is a waste of space. It is unnecessary, unneeded. You could honestly just throw it away and you would be better off, because it's just there to give you perspective. $1,250 per month, that per indicates some kind of slope. Okay? In this case, something being constant, which is really important. It then says his production costs are $37.5 per item. So when you look at this, the question is, are we doing this per month or per item? Because there's 2 different things that can happen. That's why it's important to read the last line. Write a linear function C, where C of x is the cost for x items in a given month. So the month is fixed, meaning this 1250 is a constant. It is 1250. It will not change. But this 37.5 is changing. Because we are doing it with respect to items, the equation we're looking at has to have x as the variable. And where is it put? With the 3750. If we had x in terms of months, this would be switched. Always read through your problem and make sure you have all of your components. If you miss that component, you may end up putting down the wrong pieces in the wrong place. Because when you're given a word problem like example 6, you have to make the conscious choice of, okay, what's M? What's B? And how do I plug that into my function? Anytime you're looking at a problem like this, make those adjustments. Read your parts, and you will only get better at it by doing it more. Okay? Now, this is my favorite one, and one that for some reason every year poses the most questions. Example 7 is the single best example in this assignment because of what it says right down here. This is an interpretation. It says f of 3 equals negative 2 and f of 8 equals 1. Find an equation for the function in slope-intercept form. They have not given us a picture, nor have they given us points. It would seem that none of the options we have here are available. But it turns out they did give us points. Here's option 4. What if they give me some points in function notation? These are in function notation. F of 3 equals negative 2 is function notation. F of 8 equals 1 is function notation. We're going to use that to determine the slope. Now, to do that, you need to change from function to point. We have not had any practice on this, so look carefully at this example 7. It is on page 287 at the bottom of the page. Look at it carefully. Have I said that enough times? One more. Look at it, please. It says f of 3 equals negative 2. This is a point. What we've plugged in is plugged in for x. What we get out is what our y value is. F of 3 equals negative 2 is equivalent to this statement, 3, negative 2. F of 8 equals 1 is equivalent to this statement, 8, 1. They're the same thing. They're written differently because it's checking to see, do you actually understand the notation or are you just following orders? In mathematics, we don't need dumb people. You may feel dumb sometimes. I do too. But in this case, it's just checking to see, is it actually making sense? Do you know that this function notation is the exact same as this point notation? Because if you know that, then this becomes the top problem. Plug in, find the slope. Use slope and a point to plug in the point slope form. Simplify as far as you can. It's not any harder. But because it's written differently, some of you will look at it and go, impossible. I want to go home and cry. I'm already home. I better start crying. No. Looking at try it number 3 down here. Same thing. Just giving you an extra example. F of 2 equals negative 11 means you have the following point. 2 is our x value. Negative 11 is our y. F of 4 equals negative 25. This tells me that my x value is 4. How do I know the x value is 4? Well, because if I go back to my old function notation from at the very beginning, remember, it's f of x. So if something is inside of here that's not x, it must be the same as x. So if it says f of 2, that must mean 2 is our x value. If it says f of 4, it must mean 4 is our x value, which means the other one has to be the y. There is no choice. So this is why it's 4, negative 25. All right. There's some great examples of word problems. I've tried to limit some of the word problems in our homework assignment because they take a lot longer and we need to be more lenient during this time because I know many of you guys have lives outside of school now that you are not in school. Take that as a favor. Don't abuse it. Let's go to the last part of the day. Oh my gosh, my favorites. And by that I mean the ultimate of fun, graphing. All right. When it comes to graphing, there is nothing more simple that I can say to follow these directions. Oh my Lord, I don't have to rewrite this for you, do I? Please, note the golden box. It is on page 290. Read this box, follow these steps. You cannot go wrong. You may not remember this. You've done it a dozen times, if not more. Read through these steps. There are 2 very good examples here about how to go through that. And I will be working through at least one example on a homework section I will be posting on Saturday. Follow these steps. Notice the first step they do. Choose a minimum. So they chose a 0. Evaluate the function there. Here's where they evaluated it. So notice how it got 0, outputted 5, and that gave us the point 0, 5. They then chose another function. 3. Plugged in 3, got an answer, there's another point. Then plot the pairs onto a grid. 1, 2, 3. And now you got a graph. Do not make this hard. I cannot stress that enough. This is not supposed to be hard. They have chosen 3 values, 0, 3, and 6. Cool. They chose these 3 for a very specific reason. To match the denominator. It's because it makes the math easier to do. If you're using a calculator, this is less important. But still important. Choose x's, find y's, graph points. You're done. Do not make this difficult. Okay? Now, if you're given the slope You can use rise over run to determine other point values. We've done this before. Don't say we haven't. We have. I promise it's not that different than anything we've ever done before. Rise over run. Rise, remember, tells you how much you need to go up. Run tells you how much you need to go to the right. If your number is positive, that means we go down and to the right. If your number is... scratch that. Reverse it. If your number is positive, that means we go up and to the right. If your number is negative, it means we go down and to the right. Notice to the right is not an option. It must be always to the right. Remember, left to right. We always go left to right. So, rise over run tells you we rise up or down as we go to the right. Okay, last little bit. These are some great examples of using transformations. We did that way back in chapter 2. It's worth taking a look at because I think they're really neat. And they're nicely color-coded too if you got the textbook. So please take a look at those sections on your own. Last part. Okay. Intercepts. Ooh, yeah. How do you determine what an intercept is? You have to look at the graph. Where is it crossing an axis? X-intercepts cross the x-axis, y-intercepts cross the y-axis, and the y-intercept is almost always B. The only exception to that case is if B doesn't exist, which is a totally different thing that can only happen in a select few circumstances. So, use this information. Use it to help you. All right. Horizontal and vertical. Two of the most missed things in mathematics. Let's go through them real quick. Boom. All right. Horizontal. As we look at horizontal lines, we got to have a picture. In this case, my picture is going to be done here in pink. Ooh, shiny. All right. Boom. That's the world's worst horizontal line. Let's try that again. All right. Better. All right. It's a horizontal line. Remember, horizontal, horizon, they are going left to right. Let's look at a couple different ways of seeing this line. First, the equation. This equation is y equals 2. How do I know that? Well, it never crosses the x-axis, so there's never an x value. And how do I know it's 2? Well, I know that this dot is the point 0, 2. I use the 2 to tell me what that number should be. If it had been down below, and say down here, see how it crosses the graph at 0, negative 3? Well, that would tell me that this graph is at the equation y equals negative 3. Okay, now, in terms of a table, let's take a look at each one of these as table form. In the table, we have x's and f of x's. Okay, at 0, 1, 2, and 3, this equation has a value of 2, 2, 2, and 2. We call this constant because look at these values. These values are constant. It's 2, 2, 2, 2, 2. Okay, we're like a terrible ballerina school. A lot of tutus. Down here, same thing happens. This is why these are typically called horizontal lines, as constants. Because each time you look at them, the outputs, the y's, are constant. Even if you look at negative 2, negative 1, 0, and 1, it's still the same value for all of them. And if we kept going to the left or we kept going to the right, they're still constant, which is why we refer to all horizontal lines as having constant slope. Okay, vertical. Okay, before we go on, look at our 2. Horizontal lines always have this form, y equals 2, y equals negative 3, and we can determine the number by looking at where they cross the axes. So, it crosses the axes at 0, 2, so it's y equals 2. It crosses the axes at 0, negative 3, y equals negative 3. Let's look at vertical lines. See if I can do it right on the first try this time. Ooh, that's pretty. All right. Kapow. All right. First one. Let's move it over here. Kaboom. Let's take this one. Move it right there. All right. Well, let's look at where these things cross. This one crosses at -4, 0. This one crosses at 1, 0. Okay. Now, the question becomes, how do we write these equations? Well, this one is x equals -4. How do I know that? Well, where does it cross the axis? -4, 0. Notice the number we keep is the one that's different. The 0 isn't important, the 4 is important. Over here, x equals 1. Notice that for every point on this line, the x value is 1. That is because for each of these points, the x value stays consistent. Over here, at this point right here, this dot is -4, 2. This dot right here, -4, -3. What's staying consistent? The x values. What is the x value? -4. What's staying consistent? The x values. What's consistent about them? They're all 1s. That is why this equation is x equals -4. All the x values are -4. That is why this equation is x equals 1, because all the x values are 1. If you look at the table for each of these, let's start with that first one. They're over there in blue. Okay. So notice that for these, the x's are the same number. Because if I go to -2, there's no graph. I never touch the graph over here at -2 or -1. There's no graph. Or at 0, there's no graph. So notice that for this one, the x values are the ones that are constant. But that shouldn't be the case. If you think back to all the way when we talked about function notation, functions must pass the vertical line test. They must pass it to be considered a function. This graph doesn't pass that test. It fails. This graph doesn't pass that test. That's why we consider these undefined. They fail the test. Because they fail, they are undefined. Vertical lines are always considered to be undefined slopes. They do not pass the vertical line test, so they are undefined. Constant passes. Increasing will pass. Decreasing will pass. Undefined will not pass. That's why it's undefined. This one, let's look at these functions. We got -3, we got 0, we got 2, we could have 4. Doesn't matter where each one of these is, because it's always going to have this form. The x's are the ones that are constant. It's backwards. And that's what makes this undefined. For the bottom one, same concept. So in this case, my x values are all 1s. My y values, -2, 0, 3, and let's go with 4. Let's go ahead and add a dot up there. Notice that, again, the top numbers are the ones that are constant. That's a problem, because they can't be constant. They must pass the vertical line test. It fails the vertical line test. That's why it's undefined. So all lines have this function. If you look at our two examples in the textbook, let's take a look at those. Notice this one is the equation f of x equals 2. Or as I put it, y equals 2. Because again, where does it cross the axis? At 2. Which axis does it cross? The y-axis. Y equals 2. This one, where does it cross the axis? At 2. But which axis does it cross? The x-axis. That's why it's x equals 2. Slight variations. And you can always tell from the function which one it's going to be. Look at this one. It's -4 is where it crosses the axis. Which axis does it cross? The y. So y is the equation. Y equals -4. This one. Where does it touch the axis? At 7. Which axis does it touch? The x-axis. That's why it's x equals 7. These two are some of the most commonly missed basic questions. Take a look at this little blue graphic. Take a look at each of these examples. Make sure you do not have them confused. All right. Last but not least, parallel and perpendicular. On a grid, it is only possible for these two to happen. And when you're dealing with lines, it is either going to be parallel or it is going to be perpendicular. It is possible to be neither. Three categories. The first two have simple tests you can do. If it passes the test, then it's parallel. If it passes the test, then it's perpendicular. If it fails both tests, it's neither. So make sure to always remember the three different options you can have. You could be parallel, you could be perpendicular, you could be neither. If you have a picture, it makes it easier to guess which of the two is plausible. Because from the picture, either they look parallel or they look perpendicular. If it doesn't look like either one of them, it's definitely neither. The ones in question are going to be ones where it's going to be tough to tell which is which. So make sure to use the information you have and help yourself out. How do you determine if things are parallel? Parallel means same slope. So how do we test that? Well, check. Is the slope from the first equation equivalent to the slope from the second equation? If the answer is yes, we say these are parallel. If the answer is no, check something else. Because remember, it's possible you checked parallel and they were supposed to be perpendicular. Just because you check one doesn't mean it was the right one. You could have graphed them wrong. You never know. You must check both of them. Now, once one is checked and it works, you're done. If you check parallel and it's parallel, stop. Just stop. It's parallel, you're done. How do you determine if something is perpendicular? Perpendicular means inverse slopes. Now, there are two variations on this. I'll show both. M1 times M2 equals -1. This is my preferred. I love this one. It's the best. There are other versions of this. This is the other version. I hate this version. This version, in my opinion, if I could put an X to this, I totally would. This top one's better in every sense of the word. Unless you are used to the bottom one, I suggest you use the top one. The top one is much easier and simpler to work with. Now, again, it's a test. Does this become true? When I find the first slope, when I find the second slope, when I multiply them, does it equal -1? If the answer is yes, you call them perpendicular. Perpendicular. And you stop. If the answer is no, check something else. If you've already checked parallel and it didn't work, and you checked perpendicular and it doesn't work, then the answer is neither. You cannot just say it's neither. You cannot just look at a picture and be like, aha, I am so smart. I know it's not either. No. Stop it. You must show. You must prove. Is it parallel? Is it perpendicular? Or is it neither? Notice the order. You check the first two before you ever dare tell me it is neither. We know as math teachers that you guys are intelligent human beings. We know you can look at a picture and be like, I'm 99.9% sure, Mr. Douglas. Guess what? It doesn't matter. You don't know until you prove. That is math. You do not know until you prove. And if you can't prove it, then you don't know it. So show me, is it parallel by performing this test? Are the two slopes equal? And it's a question. Do not forget it is a question. Are they equal? Yes, then they're parallel. No, check something else. When you multiply them, do they equal -1? Yes, they're perpendicular. No, check something else. If you've checked both and both of them have failed, that is the one and only time you're allowed to say neither. Now, the best way to do this is when it comes to an equation is by direct comparison. Like, you can look at these two and see, yeah, they have the same slopes. -2 and -2, same slope, done, easy. You can look at these two and be like, not parallel, not the same slope, easy. But you cannot do that for everything. If you have a picture, it's much harder, which may mean that you have to take some time to find the slopes. If you are not given the slopes, find them. It is not a threat. It is a promise. Find them or else. That's the threat. Okay? Find the slopes if you're not given them. If you're given a picture, use rise over run. Okay? Make it simpler on yourself. But make sure you can determine from a list whether they are parallel or perpendicular. Example 18 is great here as a showcase of how to do this. They've given us equations. You can see the slopes. You can determine which are parallel, which are perpendicular by just direct comparisons. But it's always a question mark. Are they equal? Yes or no? When you multiply them, do they equal -1? Yes or no? If the answer is no, that means something. If the answer is yes, that also means something. Check. All right. That concludes the day. My Lord, I didn't think I'd have to talk so much today. Whoo-wee. There's some other great examples in the text. Please look through the chapter in the book. I will be showcasing some problems from the homework that I'll be posting on Saturday. Okay. All right, your homework tonight is from section 4.1. It is on page 304/322, depending on whether or not you're using the PDF. All right. This is for today and for Friday. 1 through 53. Every other odd. Okay? And for Friday, 59 through 87 odds. In total, it's about 30 problems for 2 days worth of work. That's a pretty good list. And on Friday, we will look at the next section, which is more word problem stuff. This chapter is very short. We will finish chapter 4 next week, probably next Wednesday. So be looking ahead and be asking questions. I know this is a difficult time for everybody. I do not expect everybody to get this right away, and I know there will be some struggles. Do know we are here to help you as much as physically possible, and I will offer every ounce of help I physically can during this time. Please stay safe. Please keep yourself out of trouble, and if not, at least make sure you don't get caught. This is Mr. Douglas. I'll be signing off, and I look forward to seeing some of you guys' questions on Friday.